Hello, everyone. This is the presentation for the computational analysis course for the final project. I am Yufei Jing, and the title today is Achieving Privacy and Integrity Under MPC Setting for the Summation Computation. This is a two-member teamwork. I am Yufei Jing, and the other team member is Zhiqiang Wang. So the problem we want to investigate is under the setting of multi-clients and one cloud server. How to achieve the goal that the clients want to compute the summation of their data without losing their information, basically leaking their information to the other clients or the server, and also ensure that the final computation result is correct. The efficiency is also one question we want to address, is that each client should not take too much computation and communication cost during this process. Okay. The protocol description. So to solve this problem, we design a protocol where has 5 stages. The first is initialization, and then we have a client-cloud interaction, which means that the client will interact with the cloud during this stage, but no client-to-client interaction. And then we have an MPC initialization, which is used to generate a new encryption. And this is used for the later multi-party, which means client-to-client computation. And then we have the multi-party computation interaction, which is only limited to the clients. And then we have a final check, which means that all the clients will check the results, which they get from the MPC stage, which is the self verification, and also the result from the client and from the cloud. Which is the cloud computation result. If they are the same, then it means that computation is correct. The threat model we want to introduce is the client is honest, curious, but not malicious. The server will be malicious, which means that the server might tamper with the computation result, or the server might have made a mistake and the result is not correct. So here, the client is honest means that it will always use the correct result if it is not made by a mistake or something. And it is curious means that if something is exposed to him, for example, if one client accidentally get the information from the other client, it will use it. So it means that the privacy is compromised in that case. But not malicious means that it will not deliberately do something to it, do something to achieve the other client's data. So, and also we assume that the communication channel is secure, which means that there's no man in the middle attack or something. So in the first stage, which is by the way, starting from here, this is my personal contribution of this because I designed this protocol. So this is starting from here. This is my contribution, and so the initialization stage is that client A goes to send a message, or assume we have 3 clients A, B, C, and each client will communicate with each other to have a shared encrypted FHE and also a shared hash. Okay. Then this constitute a client-cloud interaction, which all the clients first hash their original raw data, and also append the original raw data to it to make it an array. And then this is actually considered as a polynomial. And then we encrypt it with the FIG encryption, which in our practical setting uses the BFV encryption. And then we send it to the cloud. Then the cloud computes the results basically by using the FIG addition. And this will be sent back to the clients, all the clients. Now it comes to the MPC initialization stage where client A, for example, is selected as a special client that generates a public generates another new FHE encryption where it holds both the secret key and the public key. And it will send the public key, the new encrypted A public key to everyone else in the clients. And then those clients in the MPC stage, those clients will uh, encrypt their hash message along with the original raw data with this new public key, and all the clients will encrypt this their own message with this new public key. Also for the client A, and they will all send the encrypted message to a client that is not client A. That is, we will choose from the rest of the clients to be as a considered as an evaluator or something, and then they will those selected evaluator will add the results and send the results back to all the other clients. Send the results back to the client A, which is basically the client that holds the secret key. And in that case, the client with the secret key will decrypt the message and then send it to everyone else. And then it will come to the final check where we can simply compare, for each client, we can simply compare the decrypted side result from the server and the decrypted side result from the client. So if we go back to the MPC stage and see why this is secure is because, so in the MPC stage, the only one who has the secret key during the encryption stage is the client A, for example, and all the other clients will encrypt it with this public key, but none of their encrypted message will be seen by the client during the computation stage. Only after the aggregation result, which is the submission result, is computed, then it will be sent back to the client A. And then when client A decrypts that submission result, it will only see the final aggregation result, but not the individual result, individual message of each other client. So in that case, no, the privacy is basically ensured. And how do you ensure the integrity of the data? So this is basically considered as, so for example, if the evaluation made some mistake during the client-to-client stage, it is hardly possible that the cloud, for example, it tempers the result. That accidentally tempers the result that is the same for the client-to-client result. So it is very unlikely for that to happen. And also, if both client result and the server result is incorrect, it is very unlikely that the incorrect result is the same as well. So if that happens, it means that there is some mistake and we can detect it and just run the protocol one more time. So here are some notes. For the efficiency, especially, we know that the computation burden on the final computation sum for the clients, if you only choose one client, of course, that client will carry the same computation cost as the server. So we can leverage it, we can elevate it by leverage a distributed manner with multiple clients compute the part of the sum and then aggregate together. As long as the computation involved do not involve the client that holds the secret key, basically it is safe because FHE encryption is guaranteed to be safe. And then this will save the computation time for all the clients basically, and therefore the entire verification process should be efficient. And the other one is this problem might be solved by the other possible solution, which is to consider a multi-key FHE and also absorb the hash check for it. So our FHE encryption is basically single key, which means that only one key, secret key, is held by one client who generates it. If you want multiple parties to hold a part of the key and but still keeps one FHE encryption, this is called a multi-key FHE. So it is possible that and the multi-key FHE is designed for this MH multi-party computation setting. But here we present some of the challenges. So again, we can say single key FHE alone is not sufficient for the MPC setting. Here we circumvent this scam test by isolating the client or the FHE holder who has the key to outside the computation stage. And the domain issue. So sometimes, so in our case, BFB output space is not one polynomial, but two polynomial structure. And the input space is one polynomial only. So this causes we cannot basically wrap the BFV to another BFV, and that is limited. So undefined FHE operator, this basically says that because SIS hashes the number to a array basically, and during the process, it first needs to convert number to a binary representation. And such conversion process is not defined over the FHE add. So if you want to encrypt the original data first and then do the hashing, it's kind of non-trivial to implement such an FHE operator. So we do not take that step during our protocol. Instead, we first encrypt it. Instead, we first hash it and then try to encrypt it. The lack of practical implementation for the multi-key FHE. So, after reviewing the existing work of the multi-key FHE, we see that most of the work doesn't involve the hashing process, and the only FHE incursion that involves the blind hashing, which they call in the text, is a single key FHE. So none of the existing work actually have this process, and there's no practical implementation that is found to be useful for the multi-key FHE. And the floating point issue, we point out that so basically current solution to solve this, if for example, if your input is a floating number, how do you convert it to an integer so that the input can be fed into the either FHE or the SIS? The current solution is basically to multiply it with the number of points you want to keep with 10 times the power of that number of precision, and then make it work. And SIS is also only approximately linear homomorphic from what we investigate for the materials. And this might cause some issue if since it is approximately linear. Okay, so this is a reference for what we have investigated, and that's all for my part of how to design the protocol and everything. Next, we will ask the other team member to present his contribution.
I built a simulated system based on Euphydion's algorithms and the protocol. Here, I would like to talk about three use cases. The first one is that the client and the server can verify their encrypted message or information successfully. The second one is if we have an isolated client, which means not all the client's information can be gathered or collected by one of the clients. Then in this case, because of the client lack of the information, it's unable to be verified. Another one is if we have a malicious server, the information can also not be verified successfully because the server changed one of the value, and then the client will regard that the information is incorrect. Okay, so let's get started. First, it will ask you how many clients you would like to do it. The default value is 5. Let's say, okay, let's use 5. Would you like to isolate client? Let's no right now. Okay, so here, once you choose to create a 5 clients, a graph will be created, which means so here for client 0, it's able to notify its information to client 1. As for client 1, it's able to notify its own information to 0 and 3. And then so on. It's not a full connected graph. Okay, so enter 5 numbers for a client. We try to simulate that each of the client has its true information that only known by himself. Let's use the random value here. Okay, this value will be assigned to each of the clients. Would you like the server be malicious? No, right now. Choose a client to broadcast encrypted to all the other clients. So let's choose client 1 to broadcast its encrypted to all the other clients. And then once it broadcasts, the other clients receive the encrypted, public encrypted, then it will try to encrypt the message and broadcast to other clients. Choose a client as an evaluator. Okay, as client 1 already be chosen as to share the public encryptor. Let's use the client 2 for evaluator. Once the client 2 has been chosen as the evaluator, then it will do a checksum for client side and then send a checksum, the client side checksum to all the other clients, and then all the other clients can do a checksum by comparing the client side checksum with the server checksums. Okay, so here it's verified. Now let's try to do something again. Let's say we have an isolated client. Let's use 5 clients again. Yes. So here the node 0 is unable to broadcast its own information to clients 1 and 3. So the clients 0 is actually isolated, which means that for other clients is unable to collect the information from client 0, while the client 0 is still able to receive the information for other clients. But in this case, there's we still use the random numbers and no malicious server, and choose a client to broadcast its encrypted. So client 0 actually has already isolated, so we cannot choose the client 0. Let's choose client 4. Client 4 will broadcast the encryptor and broadcast the encrypted message. Then we can choose a client to do the evaluation. Let's choose client 3. Okay. No, it's unable to be verified. Okay, let's try another case. Let's say we have 4 clients right now. Would you like to isolate clients randomly? No. So right now all the clients have been connected and they are able to receive information for other clients. Pre-enter 4 numbers random value. Would you like server be malicious? Yes. Okay, so here once if you choose the server to be malicious, it will randomly change part of the value for one of the clients. So here the client 3 has been chosen and some of the value has been changed. And change a client broadcast is encrypted. They choose client 2 and blah blah. Okay, so the encrypted message has been broadcast down, and let's choose the client 3 as the evaluator. Boom, is unable to be verified. So that's pretty much about my simulation system and about our based on efficiency algorithm and the protocols. Yeah, thank you very much.